Hey everyone, welcome to the first video from section 3.4. So in this section, we're tackling the case of repeated roots in the characteristic equation. So 3.1, we handled roots that were real and distinct. Section 3.3, we handled complex roots, and now we're handling the last case, which is repeated roots. It gets a little complicated for how to handle it in general, but it turns out the method that we can use also applies in other situations. So we'll use the method here to see how to handle repeated roots, and then we'll see how this method can actually be used to solve different problems. So let's go ahead and jump on into it. So we're looking at repeated roots in this case. So we have our characteristic equation, ar squared plus br plus c. And now if we say this has a repeated root at r1, what does that mean? Well, that means that it has a factor of r minus r1, but it has it twice. So if it has a repeated root r1, we know that this is the same thing as a times r minus r1 squared. For second order equations, this is the only way you can have a repeated root, is if it's just the constant multiple of r minus r1 squared, because it can only have two roots total. So this is the only way you can do it. Now, what is this right-hand side? Well, we can expand this out. This is a times r squared minus 2r1 r plus r1 squared. And the important thing I care about is this middle term. So if I write this out, ar squared minus 2a r1r plus a r1 squared. The important thing I want to note from this is this relationship here. Because what this tells me is that since these have to be the same polynomial, this tells me that b equals minus 2a r1 or r1 equals negative b over 2a, which may have been a formula you've seen before for the bottom vertex of a parabola, and that's the formula you get for it there. So it turns out these things are going to be important when we start trying to solve the equation. And we'll see where they show up in a little bit. So let's go back to the beginning. So we're going to use that fact in a little bit. So we're trying to solve ay double prime plus by prime plus cy ay double prime plus by prime plus cy equals 0. And ar squared plus br plus c equals 0 has a repeated root at r1. Well, so it has a root at r1. So we know y1 of t equals e to the r1t is a solution. We already know that. The question comes into, how can we find another one? Because we need two, as we need two in all the other cases, to get all of our solutions that we want. So we need to find a second one. How can we do that? And the way we can do that is by reduction of order. So how can we find a second one? And this is called reduction of order. And so we'll do the method here for this particular case, and in the next video I'll talk about sort of why this is called reduction of order and how it works in general. So the idea is, let's look for a second solution of the form y2 of t equals some function v of t times e to the r1t. So we're taking the solution we already know, this e to the r1t, and we're going to multiply it by, instead of a constant, by some function of t. And we're going to try to use this to see if we can figure out what this v of t should be to get our second solution. Now we're going to want to end up plugging this into our ODE to get the solution, so we're going to need first and second derivatives of this y2. So let's do that right now. y2 prime of t, this is a product rule again, is going to be v prime of t e to the r1t plus a v of t times r1 e to the r1t. y2 second derivative is going to be a v double prime of t e to the r1t plus a 2 v prime of t r1 e to the r1t. And that comes, the one comes from hitting the derivative on the e part here. The other comes from hitting the derivative on the v part over here because they end up being the same. And then plus a v of t r1 squared e to the r1t. Cool. Now let's plug all this into the ODE and see what we get. So our ODE was AY double prime plus BY prime plus CY equals 0. And so I'm going to get 0. I'm going to flip the equation around. Equals A times Y double prime, which is V double prime of T e to the R1T plus 2V prime of T R1 e to the R1T plus V of T R1 squared e to the R1T plus a B times V prime of T e to the R1T plus V of T R1 e to the R1T plus a C V of T e to the R1T. And now what I want to do is I want to group all the terms based on the order of derivative they have in V. So group the V double primes together, group the V primes together, and group the V's together and see what pops out of that. Although first, to make things easier, I can get rid of all of the e to the R1T's, right? Every single term has an e to the R1T in it. So I can just divide that out. We'll be happier in the bit once we realize we can do that. So let's group all of the V primes together, all of the V double primes together, and all of the V's together and see what happens. So 0 equals V double prime of T, and that only shows up once, and that's why it just has an A next to it, plus a V prime of T. What does that have? That has a 2AR1 plus a B. So the 2AR1 is this term, and the B is this term. And then plus a V of T times what? AR1 squared, that's this first term, plus BR1, that's this term, plus C. Now what do we notice here? So we said that R1 was a root. This is exactly the characteristic equation right here. So this is 0. We also noted way at the beginning, I told you it was coming back, that B equals negative 2AR1, which means this is 0. So all of that nasty work, and what we come to is simply that V double prime of T equals 0, which if you integrate that twice gives me that V of T is just dt plus k. I don't want to use a and b because we already have those letters floating around, but it's linear. That's all V of t is at this point. So what is our solution? Our solution, y2 of t, was V of t times e to the r1t, which is dt plus k times e to the r1t. Now, since I just want one solution, I can take d equals 1 and k equals 0. So first, I can take k to be 0 because my y1 solution is already e to the r1t. So if I put cy1 plus c1y1 plus c2y2, I can just take the k part from the y2 and shove it into the y1 equation, just change that constant c. So I can forget about the k, because I don't want to, and also I forget about the k because I don't want to get my original r1t solution back. So I'm just going to get rid of the k. And since the constant times t, I can just get rid of the constant because I'm going to put a constant there anyway. So what you want to think about is my solution here, my y2 of t, is going to be t e to the r1t. So in general for these equations, you don't have to go through all this work. All you do is multiply by t. That's really all you have to do is multiply by t for these constant coefficient linear equations. That's all you're going to have to do. So my solution before was e to the r1t. My second one is going to be t times e to the r1t. And we know this solves the equation because of how we set up our work. This will solve the equation. And if we check the Wronskian of these two guys, the Wronskian of y1 and y2, in this case, is going to be e to the minus 2 r1t. Again, not 0, so we're good. We found a second solution of the form t e to the r1t, so that the Wronskian of our original guy and this guy is non-zero, which means I found two independent solutions. So my general solution is y of t is C1 e to the R1t plus C2t e to the R1t. And that will get a red box. So that's how we handle the repeated root case. Basically, because you don't have another solution of the form e to the RT because you already have that one, you get a new one of the form t e to the R1t. All right, so that's it for this video. I'll give you an example to do real quick to write the general solution out. It shouldn't be too hard. These guys are pretty easy because they have to be perfect squares. But we'll do that, and I'll give you that to look at right now. All right, there's one for you guys to work on. Just find the general solution for that. It shouldn't be too bad once you write things out and use the stuff we did before. All right, thanks a lot for watching. The next video is going to go into this reduction of order method a little bit further and how you can use it in different situations than just this. Thanks for watching, and I'll see you in that one.